an algorithm that let's do a little warm-up exercise today about an algorithm that I found on the internet yesterday, which generated quite some interesting visual artifacts, and hence it's related to computer vision because it tells us a little bit about the human visual system. So the algorithm is quite straightforward. The idea is that we have some image, and a tree, and we want to replace it that image in grayscale we want to do some operations to try and modify the image so that we get a better understanding of the geometry. And so this algorithm is actually kind of neat. You break the image down into grid, into various blocks. Now each block, you calculate the average brightness and then it's kind of like a dithering algorithm. So given the average brightness, you replace that block with a square that is black, where the size of this square, or this shape, actually matches the average brightness. So if it's white, then you draw a very small square, a zero-sized square. If it's black, you fill in the entire square. If it's grayscale, like 128, you would make it a 2 by 2 square, something like that. So basically, the image will run it, and then you'll see what the image looks like. It's kind of like a grid-based image then, where you approximate the brightness values with the size of the square. Now, in order to implement that binning function, you need to have an image. Then you need to have the size of the grid. Now, the implementation that I saw, they used squares, but we could also think about this as rectangles. So we give it a different grid width and grid height. Maybe we go grid height, grid width. And then there's a separation, which is the padding between those squares. So if you want to have guaranteed a white border around it, then you can add some padding to the, so let's say 2 pixel padding. Like this. So before you start implementing this, what else would you need to think about?
The the average brightness here is just like the average of any block, or is it like a average of 9 adjacent blocks?
The average brightness would be the average brightness in this,
Oh,
all the
oh,
pixels,
I see, I see.
all the pixels in that block, the average brightness.
Okay.
And by doing that, one thing that we can do is it's easier to detect colors and things like that,
Yeah.
or objects,
Yeah.
because noise will be averaged out in this case. I'm not sure about the scaling. Like, we have the average brightness, right? Now that could range from 0 to 255, right? And then if we have and this is the interesting part about this algorithm, if we have a 8 by 8 square, right? If our grid width and grid height is 8, then we basically have 8 different patterns we can draw. 1 pixel, 2 by 2, 3 by 3, 4 by 4, 5 by 5, all the way up to 8 by 8. So then first I thought, okay, we take the image and we calculate the maximum and brightness of the actual image, right? But I think that may be wrong. I think you need to scale it from 0 to 255. Because 0, then black would be 8 by 8 square, right? And 255 would be 0 square. So just a dot. So then you would get 8 different brightness levels here. So that should be 16, right? 2 to the 4, 33, 32. Yeah, 32 levels. So 32 would be, since it's inverse, this would be a 7 by 7. 64 would be a 6 by 6. This would be a 0. So 220, 256 here really. Then 3224 would be 1 pixel black. So that's one thing. The other thing is, I'm not sure how to deal with like it would be nicer if it were only sizes 1, 3, 5, 7, right?
Right.
so that you have a defined center position for your square. But I don't think that's so good because here the sizes that we get, then we only have 4 sizes that we can draw. Otherwise, at least we can draw 8 different layers. So I think we try the 8 one first. Okay. So we want to implement this binning algorithms that I found on the internet yesterday. And the idea is to take a region of size grid height and grid width, calculate the average brightness, and then replace every block with a square that is of the color black. So at the end, your image will only have 2 types of pixels. It will be a binary image. It'll be either 0 or 1.
What is the algorithm called again?
Pardon? Binning.
Binning.
Yeah.
Done for, like, the purpose is...
It's, the purpose is to practice some image manipulation and computer vision algorithm.
Okay.
And it provides a pretty nice visual effect.
Okay.
So that's why I like it. So it's a warm-up exercise for today.
So we can't predict what the final image will look like. It's depends on the
Image input.
Oh, it definitely depends on the image input, but also it depends on. I mean, I've seen the image. It looks kind of neat. It's an interesting effect that you get. Especially if you vary the grid height and grid width and the separation. But before we start that, I want to get back to last class because I think I actually made a mistake. Because last class, when we were talking about the fact that for image function, there is no analytical solution of the gradient because we don't have a function, right? We have the response from the sensor. And we were talking about if this is cosine, or my image function would be cosine x, then the derivative would be. And at that point, I said, okay, I'm not sure what it is, but I trust you, right? Right? Which is actually, I think, a wasted opportunity for teaching. That's not what I should have said. So we will go back in time, and we'll do this again, and then I'll tell you what I should have actually said. So cosine x, so I'm not sure what that is. Then you say negative sine x. And then I say, oh, are you sure, right? And the point is, even without doing a lot of analysis, I should have checked that answer. And I think it's important to sort of realize that mathematics is not something that you need to sit down and have like 3 hours to go through a calculus textbook or something like that. It's actually, if he says negative sine x, right, it's the derivative of cosine x, then how would I check that? That's my point. You don't need to, yes, I could do this, right? I could limit of delta x towards 0 for cosine x plus delta x, right? But that's not something I can do in my head.
Oh, I see.
Or at least I can, maybe you can. But that's not really necessary to just sort of give it a cursory check to see if this is actually correct. Let's have a look at what does cosine look like.
Starts in 1,
Yeah, starts at 1, then
down to 0. Down to 0, then -1.
this is the cosine function, right? And how is this graph generated? Why does it look like this?
Circle.
Because it's a circle
Unit
of
circle.
unit length,
Yeah.
right? And it's this part here that we're interested in. So let me change that. Instead of starting with cosine, we'll start with sine.
Alright.
Just so that the graph, otherwise I have to rotate it,
Yeah.
plot it down there. So let's start with sine x, and then you would say that should be cosine x, right? Then our graph looks slightly different.
Starts at 0.
Starts at 0, goes at 1, and pi over 2. Then drops down to -1 and then 2. Right? And yeah, it doesn't look like that. It looks more smooth like that. And that occurs because I have different angles here, right? And that's this height. The height of this pointer is what I get. That's what draws my curve. So at pi over 2, we're at 90 degrees. Right? So what do I actually mean when I talk about the sine and cosine of the derivative of sine and cosine? And by the way, if I want to draw the cosine, then I best draw it like this: +1, -1, and then it will go 1 down to 0. Right? That would be the projection for the cosine. Like without thinking about limits, what does the derivative, and this is quite important to get maybe a more intuitive understanding of what the derivatives mean in lots of areas, including computer vision, engineering in general, and robotics in particular. The slope, right? Yeah. So it's the slope of this function, which basically means how quickly that function changes, right? So if I want to think about that, then I'm asking here, if I move by a little bit, by a small angle, and then this is the angle here, x, then how much do I go up? Because that's the sine, right? The sine is how much I change in this axis. The cosine would be how much do I change in this axis. Right? And then, if we zoom in on this, and I interpret the angles as radians, right? If I take the angles in radians, if I think about the angles in radians, what is the radians of an angle? That's the arc length, right? And how much do I go up if this is how much I move here, right? How much would I go up? Well, the point that I would go up here would be this. Right? Now, what should the derivative of sine dash x actually be then? That would be basically almost the same, right? Because if x is small, then it has to be very close to 1. Like this distance here, it's a little bit smaller. Sorry, this, if I grow out further enough, this is going to be a bit smaller. But if it's here, and we just look at tiny, tiny differences, and there's very little difference between the arc length and the actual just going up part. So that means that at this point, our derivative must be 1, right? Because I change, and this is actually the sine approximation for small angles, right? That's commonly used. So often, if x is small, you can replace sine of x with x, which simplifies a lot of the. There's a common abbreviation that people know. Even if you don't know that, it's clear that the derivative here of sine x, so sine dash x, has to be 1. And if I get to this point here where it's 90 degrees, it's also clear for similar reasoning that it must be 0 at this point. Because we go up and so we have a maximum point here. If it's a maximum point, then our derivative must be 0. So now, even without, especially without doing any limits, I can sort of say that the derivative of this must start at 1, and here must be 0. As it continues, it goes down to -1, and then 0, and then 1 again, if I follow all the angles. Right? So I get this curve. And then if you know that you only have that the derivative is of the form sine or cosine, then it has to be the cosine. You can even do better than that. Having done this analysis, we can sort of think and say, okay, if I'm at an arbitrary angle, then how does this point move? What's the tangent of this point? Because in order to calculate the derivative, we need to calculate the slope, which means we need to calculate the tangent of this particular function, right? So I can draw this one here. So this is angle alpha. That's sorry, not alpha, x. This is angle x. So what's this angle then here? The angle of our tangent, which is the angle, which is our derivative, right? What's that angle? This is 90 degrees, so this here must be 90 plus x. Or pi over 2 plus x. Right? And then how does this value here change? Well, the movement that we change, our sine is this part here. And we looked at that already. That's a cosine that where this changes at. Right? Because this would be the sine of this angle. This changes with the sine of power 2 plus x, which is equal to the cosine of x. And this part here is how the cosine changes.
Cosine pi over 2 plus x.
Yeah.
So that's
But here we go negative, like we decrease. Right? So this will be negative sine x. So my point is that you shouldn't just focus on the formula. You should focus on the understanding of what it is that you're actually trying to calculate. And I think so. It was a wasted opportunity to actually showcase that even though you may not know what the formula is, you can get pretty far by just thinking a little bit about what the derivatives actually are and which direction they have to be pointing. And I think that can be very, very useful because it gives you a nice, better insight into many problems. And even if you run into a hurdle eventually, you then are in a much better position to understand this particular formula if you do look it up with Google or something else. There's actually a nice PDF that I found one time by a guy from MIT. MIT calls it the street mathematics. And that's kind of a play on street fighting, right? Not according to any rules, but trying to get at least a little bit of an understanding of what the problem is all about. Another example of this would be if I ask you about the motion under constant velocity, constant acceleration, motion under constant acceleration, then the formula is S is equal to right? S is equal, so the distance is 1 over half a times t squared, right? Now you may remember that, or may not, but if you need to know what that actually is, one nice thing you can do is to just check if this formula actually makes sense, right? And then what it actually says. So one thing to do that would be to check the units. So S would be a distance, right? So there would be meter. So meters is 1 half. A is an acceleration, so that's
meters per second squared.
Meters divided by second squared. And time is seconds. So time squared is second squared, right? So now at least our units make sense. If you write square root of a here, then you know something is wrong, right? Because your units don't work out. You'll have a square s here instead of a s squared, so t squared. So you end up with the m is equal to the square root of m divided by multiplied by s, which is wrong. Right? So checking the units is important. And just by looking at it, then you can sort of realize, well, actually, what is this doing? I'm going, I'm moving, and the distance that I cover basically, the speed that I have at time t would be a times t. Right? Now, the distance that I cover is the distance multiplied by the time, right? The velocity multiplied by the time. And that sort of means that under constant acceleration, if we start at 0, and sorry I didn't say that, but we start at rest, then our velocity, the effective velocity at which we travel, there's sort of the first part where we're below the average, and then the second part where we are above the average. So now we proved the sine and cosine, sort of at least informally. If you want to, the mathematicians, they do it a lot more formal than just drawing the diagrams, but that's correct. Of course, sometimes you can't do anything else. Like if you, what's the derivative of x squared? 2x. Right? If you want to prove that, then I don't know any way to do that graphically, like sine and cosine. So then you really have no choice. Then you end up with the limit of
delta
x squared x plus delta x squared, right, minus x squared over delta x. That's correct. So then that gives us x squared plus 2x delta x plus delta x squared minus x squared divided by delta x. So these two cancel. Delta x cancels. Delta x here doesn't cancel. The square cancels. So then we have 2x plus delta x, where delta x goes to 0, so that will be 0, so then we end up with x squared, the derivative being 2x. So that's okay, that's a correct proof. I think because you're only doing arithmetic manipulation, it's less intuitive, less insightful than this kind of analysis or graph or something. And of course, there is a way to do the algebraic derivative of calculating sines, derivatives of sine and cosine as well, which is what the mathematicians prefer, but these kind of geometric proofs, I think, are very interesting, not very interesting, very useful to give you a sort of a more intuitive understanding of what actually is going on, why the cosine of x, the derivative of the cosine of x is negative sine of x. So I kind of like that, and I think that's what I should have said last class, instead of just saying, we just assumed that it is. Now, last class, we didn't really care. I just wanted to say there is a derivative for cosine x. There's no derivative for what my camera sees when I take a picture of Taipei 101. If you have a chance, I recommend this. I'm not sure if it was a course or PDF, but the Street Mathematics is quite a clever way, and it has lots of examples of where this kind of back of the envelope analysis makes sense, right? Or how to apply that further insights, and it's kind of nice. Okay, good. So now I'll give you 30 minutes to implement your binning algorithm. So take a picture and then bin the image, separate it into rectangles by grid height and by grid width. And then you can add some padding by adding a separation around it. Then calculate the average brightness for each grid width, grid height region, square, or rectangle. And then put that, put a black square with the correct size in that location. And then you can think about conversions or extensions to color images, but right now we just start with the black and white image.
Can I take a picture of the whiteboard here?
Sure, yeah, yeah. And you don't have to use the Jupyter notebooks to implement that. If you want to use your Python, local Python installation, then it's easier. That's really fun. Oh. So here's what the thing looks like where I found it yesterday. So it's kind of cool, especially if you have some. So here you can change the size of the bin.
Oh, it's really cool. Yeah.
It's pretty neat, eh?
Yeah.
Like not bad. So it's a nice programming exercise. As your bucket size becomes too small, you can sort of see then it becomes difficult for the algorithm because if I only have uh, size 1 square and 2 by 2 squares, then there's only two different colors that I can basically paint, right? So here, this one looks more like a single dithering, and then here it kind of starts adding more. And then as you go too big, then of course the resolution disappears. Right? But this kind of thing may still be useful if you deal with um, detecting objects in the wild. Like if you want to do that very fast, then this would, since these are, you could replace this with the average brightness in like low regions, for example, or collect all the size 8 squares that are connected to each other. So we can see if that will be, that will allow us to detect the walls in the obstacle round competition. And then here, this is the gap size, so you can increase the white space around the grids. But I think the gap size smaller is kind of nice. Okay, how come it's in Chinese? So here's the description of the algorithm.
Oh, where is it?
It's on here. I'll just post it.
Thank you.
And it was posted yesterday on Hacker News with a kind of nice visual.
gonna call it default separation.
So first, I'm gonna generate a function that just takes the image and breaks it down into the individual grids. And now I want to process each grid separately. So maybe I just print out the shape. And what size did I use? Hope that Google gives me enough processing resources. So grid height, grid width is equal to 16, 32, let's say, just to check that it actually. So if we look at the output here, we can see it actually takes the image and it returns our cells. They're 16 by 32. But now we have to deal with one problem that at the end, all of a sudden I have a 20. Okay? And that's because the image width doesn't cleanly divide into 32. Right? So somehow we have to deal with that. Let's worry about that later on. Let's do the other parts first. If I look at that code, how do I mean, it's pretty nice, right? It gives me each grid now separately. But if I want to return them to my calling function, then what would I have to do?
Do you put them in an object?
Into an object or into a list?
Oh, yeah.
So I would have like the grid. So that means I would take the entire image and then break it down and put all the cells into one list, then I return them all at once. That can, if my image is huge, that could cause a problem with the memory, right? Because I need to have, if my image is 10 megabytes, I need another 10 megabytes basically to represent that list, 10 megabytes plus some overhead, because now instead of having a 2D array, I have a list of many small sub-arrays. What's the better way of doing this in Python?
Reference?
No, Python doesn't have any pointers or anything like that, if that's what you're thinking about. In fact, the image will be passed by reference, anything but the primitive object data type, anything except pods will be used by reference. So I could return the coordinates, and then I don't need, but then that would still be a little bit cumbersome. The nicer way to do that is to use generators, which are one of the advanced features of Python, but it works really nicely in this scenario, right? Because I can yield the grid, and then at the end, I return. So now, a generator is like a return. The yield call is just like a return, except when I call that function again, the algorithm is going to continue after the yield, not at the beginning of the subroutine. So we yield one. When I call get grid again, I don't go to the top, I end up here. Right? So I can now just implement this. And maybe I'm gonna fix that, but for G in get grid image grid height grid width.
So with this part, we're drawing the width.
No, right now we're not drawing anything. I just want to get each grid separately as a little 2-bit bitmap. For one thing, that'll make it easier to calculate the average. And here now I don't need to create a list. I only get one element at a time. And the output will exactly the same as before, except now I can get each grid. Now, I think I also want to return the coordinates where that grid came from. So here then it says this came from row 784, x coordinate 736, 768, 800, 832, 864, so on and so forth. So now we have basically everything in place. I can calculate the average over G. That will give me the average color. But I want to now you can see one thing about that particular image. It looks black and white, but actually it's a color image because there's 3 color channels here at the end. If it were a grayscale image, a pure grayscale image, then we would actually only have one number here. But the way I coded it, by just taking the first two axes and the first two axes here, this will work with color images or with proper black and white images. Like I can try this, we should get the same result. If I just take the green channel, then it's a proper black and white image. And then the first part, we get the red, green, blue components. And then for the second image, we just get the one number, which is our average. So this is the number that we want. And the first part of the image, it's a 3D. So with some thought, when you code, it's easy to implement algorithms in Python that work for both color and black and white images the way that you would expect them to work. Then we can try out the binning algorithm later on with colored images. So now I have the averages, and hopefully you have them too. So I don't want to print all that much. So here, this is a pretty nice get grid function, pretty useful. Then I generate an out image. And actually, that out image, let's make the borders all white. By default, the thing is white. The background color is white. Here's my grid and the average color. And actually, I could just plot that with this image.shape. So if it's a black and white image, we get a black and white image out. If it's a color image, we get a color image out. Now we have our axis and our average. So then I need to calculate the size of the rectangle, because I have grid height and width separately. So I need to figure out how to map the brightness to some kind of rectangle size. Right? And clearly, if it's 0, then the size should be 0. And if it's, if it's 1, if the brightness is 255, then it should be no black at all. And if it's 0, then it should be all black. So now we need to figure out a way to calculate a size given any value in between here. So if you want to grow a rectangle, how would we do that? I want one block, and it should always be a rectangle. And the blackness should correspond to the color. So then I think we need to first figure out which one is the min and the max of the grid width or grid height. And then and then I would say that we start at 0 and we keep adding this many blocks. So what sizes can I build if my minimum is 4 and this is 8? Then I can do 1. And then I think the second one should be here or here. That's a question. If I have a brightness value of 2, then I could do it here or there. Once. And I want it to be mostly square. So let's say I have a value of 4 and 8. Let's say I have a value of 12. Then I could say, we'll take the square root of this. Which would be 3 point something. So then first I make a 3 by 3 square. And then I have to add an additional 9. Then I have to add an additional 4 pixels. So then I would add 1 here, 1 here, 1 here, 1 there. Because I don't think, I could just do it like this, 1, 2, 3, 4, 5, 6. But then I think it'll look a little bit weird. instead, I try, and of course you can come up with your own idea for how to add the pixels. Or just make sure they're always square, then that will be easier. I can say I do 1 by 1, 1 by 2, 2 by 2, 2 by 3, 3 by 3, 3 by 4, 4 by 4. So then I would go 1, 1, 2, 4, 1, 2. 4 by 4, 4 by 5, 5 by 5, 5 by 6. Yeah, I think I want to fill it up like that. So I need to somehow decide what the pattern is. So first let's calculate the number of pixels. How many? Min axis is equal to, or if grid width is greater or equal to grid height, then min axis, max axis is 0, 1, else min axis, max axis is 1, 0. Okay. So I want this rectangle, so I can only add one entire row or one entire column. We don't want to add individual pixels. So yeah. So I have those options: 0 by 0, 1 by 1, 1 by 2, 2 by 2, 2 by 3, 3 by 3, 3 by 4, 4 by 4, 4 by 5, 5 by 5, 5 by 6. Min axis size. 0, and that would be great. So the number of entries that I have first is I go up to where my limit is with the minor axis, the one that I have fewer options to draw. So there then I have 0, I only have 1, 0. So that would be the min axis size. Multiplied by 2. Right? I have those possibilities. 0, draw in. Then we have 1, 1 by 1. Then I can either do 1 by 1 or 1 by 2. If I have 2, I can do 2 by 2 or 2 by 3. And then I can do 3 by 3 or 3 by 4 up to my minimum axis. So that's those 4. Minimum axis would be 4, 8, 8. The min axis is 4. But they could be equal, so 4 by 4 may be the largest one that I can do. Okay, so If I have size 1, then I can only plot 1. Yep. If I have size 2, I can plot 1, 2, 3. Yep. If I have 3, I can plot 1, 2, 3, 4, 5. And now the square is filled up. So now I can add only the difference between max axis size minus min axis size. And now I can just fill it up with those sizes. So with 4 by 4, once we get to 4, then all I can do is add 4 pixels, columns of 4 pixels, until I reach 8. At which point then my whole grid will be filled up out. Okay, so these are the number of levels that we have. Right. So now that particular image, I know it's uint 8, so it's one unsigned byte, so the values go from 0 to 255. So that means that the L is equal to 255 integer division divided by the number of levels. This should be the same. So now we have the level. So now we need to figure out how to plot that rectangle. It's much easier if you do squares. I should have not started with rectangles. A little bit too ambitious, but now we'll push through. So what are the sizes of these, and how do I plot them? So now I have the level 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I just need to figure out what kind of rectangle to draw. So it's either square, everything we draw is either square or square plus 1 until we have too many left over. So the level min would be equal to the level divided by the min axis size. the next one, the larger level, would be this, the remainder. Oh, block min, go to level min. And I don't think, like getting the industry that really helps. So I just need a flag for the swap. Level is okay. Let's see what we get for numbers. So here's our average. And actually, this one I could take outside of the loop. Right? That doesn't depend on the. Oh, it may, because at the end the sizes will be different. So let's have a look at that. Setting. How come I'm setting average? Inhomogeneous array. This image. $7.99, 1173. That's correct. G is not G anymore. It's G, Y, X. So now it says that my image here is 112, and I have 48 different levels if I want to allow 16 by 32. So let's make that smaller so I can follow along easier. 4 and 8. Oh, 4 and 4. It should be easier to reason about. How many levels do we get there? 8. Then we get 8 levels for 4 by 4. How do we get 8 levels? 1, 1, 2, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 9. 1, 2, 3, 4. And the 4 by 4. 1, 2, 3, 4, 5, 6, 7. Plus 0, plus none. Yeah. So that seems to be correct. Level 31. That's not the level, that's the increase in levels. So the level in the level is the level is 255 divided by the average. And there now I need single number, so I can take the average. Let's just take the green channel, then it's an average, it's a single number, then I get 255 divided by the average. But then what happens if the average is 0? That's not correct. It's the average divided by 255 multiplied by the number of levels, right? Yeah. And I think I want that as an integer. Or master floor, which does the same thing. Now we get some level 5s, level 6. So if it's very bright, then we get level 7. If it's 255, we get level 8. That's correct. If it's level 4, we have level 4. Level 5 is 182. Oh, 13, 11. 11 is level 0, so okay, that's good. So now I need to calculate the number according to the minor axis and the major axis. So I think let's print those out too. So in this example then, if I have any level 7, then how do I decide where to draw it? How would I decide what these numbers are for each level? If this is level 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth. So that means the number of is a level divided by 2. Yeah, because there's 2 there every time. So the level minimum would be the level divided by 2. It's 0. If it's 1, 1 divided by 2 integers. So level plus 1. Or mass dot ceiling of that. Level plus 1 divided by 2. Then if it's 1, it's 1. It's 2, 3, 3 divided by 2 is 1. And 3 is 4, then it will be 2. Okay. Then the level max should be so now I have level min and that's always a square now. So if I have 2, I'm at level 2, then level plus 1. No, divided by. Now I just need to figure out if it's this much or one more. So how do I decide that? If the level divided by 2 greater than 0.5, no. 0.5. Yeah, so it seems to generate reasonable rectangles now. 1 by 2, 0 by 1, okay. Um, 4 by 5 for level 7. 4 by 5. And then I need to invert them. Yeah, so there should be 1 minus. Because if it's 0, then it should be all white. If it's white 255, then the size should be 0, what I want to plot. So we have that, so now so if the grid width is greater than or equal to the grid height, then I just want to plot a rectangle so that out y to y plus oh, grid height. G height, G width. And this probably should be G width here because at the edges we dropped for pixels. And then this means number of levels is that. So now I set this to 0. I calculated the level min, the level max. Now in every grid, I'm going to position it at the top left now, instead of in the center, but we can center it afterwards. Now let's just have a look at it, see what that image looks like. I'll be surprised if that actually works. So for your own implementation, you can just use squares. It's a lot easier to use squares. And here's the problem, because 4 by 4, and it generates 4 by 5. See if it at least calculates roughly the way it does. And then I just want to plot it. So we create an axis object, and then we show our output image. Oh, not so bad. But I think my calculations for the minimum axis are not quite correct. Because it's those shapes here, the number of squares. So let's see how far you got. And how do you calculate?
Actually, just follow.
Oh, okay. You're supposed to do your own version.
I assume not just all this one. I heard this is the usual simplified version, which will come down. This is improvement.
Okay.
The original, can you guess the original image? What it was?
Really?
No, you're right. It's this one.
Okay, but that will be kind of hard.
Oh, yeah.
We didn't have enough. Your grid size, I think, was too big. If you go back to your image,
Yeah.
what you have is okay, but you don't have much fine details.
Yeah.
You guys have? Huh? Okay, but this is JavaScript, right? This has nothing to do with Python. So you converted it to Python? Okay. And then you get this. But you only use squares, right? Okay. And then how do you calculate the linear? Yeah, okay. That gives you the level, but how do you determine how many different columns to do for each? Okay, but that's just what I have as level here. So that is correct. Okay, so there you calculate the average, and then full one is full. Yeah, understand. So that's so where does stop y come from? That's just the edge of the bucket. Overriding the machine. That's good. So show me your image again. And let me see the code. That's very nice. Yeah, so you keep increasing it just as a fraction as you go along. Yeah, that's actually also a good idea. So instead of figuring out exactly these sizes, you can sort of say that we keep the same aspect ratio and we just go along this axis then. That's true, yeah. That's a clever way of doing that. Much better than trying to figure out the exact sizes here that we have. Um, and it looks nice in your image. So well done, good job. So we can just say instead of spanning a square, we span a rectangle, and then the level decides the size of that square that we make. That would give us, that would do a better job. This one here, it gets really too complicated. It's hard to follow through. Um, this should do exactly the same thing here. Still, I would have liked to fill them out first. In this pattern. I like this pattern of adding them. So instead of doing it this way, I simply set the min axis and max axis based on the level that I have. So here then the number of levels that I have will be G width is greater. Oh, that's well, that is wrong. It should be less than greater than or equal. It should be G height, G width. I have one line there. G width, G height. And then I just use one fraction to number of levels will be G height. Then And I think I can do it with just a single out statement here. Out is equal out of y plus and this, then I don't really need that as an integer, I need it as a fraction. Level from y to y plus level times g height from x to x plus level times g width equal to 0. And I think I need to convert that to an integer. So that's a little bit cheating, but it works. I didn't want to print all of this. Actually, not that much difference. Yeah. Has some more of the very small highlight in the middle here. So that's because I didn't deal with the fact that in my previous implementation, I didn't deal with the fact that we have 4 by 4 and then I can have multiple columns here to still go across, which is different from what he implemented. But that's also a nice idea. So we just grow the level in both dimensions. So this one here is grid height. This one, sorry, this is grid width. This is grid height. And then we move along these two axes based on the level that we're at. So if we're at 50% level, we go 50% in the direction of the x, and then 50% in the y. That's a lot easier than trying to figure out this part here where we do 0, then 1 by 1, then 1 by 2, 2 by 2, 2 by 3, 3 by 3, 3 by 4. Actually, up to here is not so bad, but when you have to deal with the remaining part, once you have the maximum in the minor axis, then you keep adding additional columns in this case, or additional rows. Then that's a special case that I hadn't tested for before in the code. So here we have 4 by 4, so let's try some other ones. Some bigger ones, so 16 by 32. Yeah, now think here that should be +1 really. Like if my input image is completely black, input image is completely black, and I can pass in the data type that I want, unsigned byte here, for example, and try this with image 2. Oh, okay. How come? Oh, because out is too big. Out is image 2, the out 2. So here we can just test, right? If the image is completely black, then I don't want any white borders there unless I specify some padding, which we can add in later on. So then it should be completely black. So that's okay. And then if it's 50% black, then multiplied by 128. Come on, I have a yellow image. Multiplied by 1. Oh, because the image is too big. Make that 64 by 64. Yeah, so then it plots those. So why? Uh, yes. The Anybody know why the colors are off here? That's because if you use Matplotlib to plot a grayscale image, then it actually uses a color map, a false color map. So if you wanted to print as a grayscale image, then you need to specify the color map. So where's my IM show? And then CMap is equal to matplotlib dot color map gray. Oh, CMap is gray. Okay. So now it's black and white the way it's supposed to be. So now we have no border if it's all zeros and if it's all one. Ah, then we have a little off by one error because it still plots out ones. Oh, because I set it to plus. How come 255? So this is 0. be all 255. So 255 0. Y to Y. So why is this? Black. So we can have a look at small subfield of our image. That's also quite useful for debugging. Of because the floating point number, when it interprets it and it's between 0 and 1, then it's going to be mapped as a grayscale from 0 to 1. But if it's exactly 1, then it thinks it goes from 0 to 255. So if you have an image as a floating point using floating point numbers, basically Matplotlib tries to guess what the correct range of the pixels are, and if it's between 0 and not up to but not including 1, then it thinks it's a fractional image. If it's above 1 or equal to 1, then it thinks it's an image that ranges from 0 to 255. So here, maybe it's better to divide it by 256, and then that shouldn't be a problem anymore. No, we have now. No, that's. How come that level is so long? 1 minus 255 divided by 255 should be 0. So let's go with 200. Mostly white now. to 1. I think, not sure what happens here, but let's try something else. Out 1 to 1. 0, 0, 0. But yeah, it's 1. It shouldn't paint it as white, but this one here takes it as, it's basically a rounding error. This one here takes it as 1, which is why this is above 1 or equal to 1. Why is it? It does some kind of scaling here. If the entire image is 1, all of a sudden it shows up as black, which is bizarre. But that has not, it's not the code that is a problem, it's the matplotlib plotting library. If I don't give it, if I just set everything to 1, I think it's scaling it to try and paint it from the minimum to the maximum, but if everything is a 1, then it just assigns a color of 0 to it, which is a little bit weird. So if you want to plot a grayscale image in matplotlib, I guess I'd have to convert it to uints. That would solve it.
we have all two. Two. And we get big squares.
So it's just if I do it with a synthetic image that has no range, then it gets Matplotlib decides to paint it in black then instead of white. Okay, good. So that's it for today. That was a little Python programming exercise. Now, the second part of the class today will start at 3:30 online with the German students.
Okay.
So we have I posted the schedule for the Global Virtual Classroom on the Discord server. You can have a look at it. Today I will talk a little bit more about color detection in the computer vision part. But most importantly, you'll have a chance to get to know the students from Germany and Professor Gant. Then hopefully today we'll do a little introduction of the various teams. So try and find a teammate.
So ideally how many people?
It'll probably be 2 from Germany and 1 from Taiwan.
Okay.
Yeah.
All right.
So that we.
They're
They're about twice as many as us. That's what they told me. So we'll see today how many will actually show up.
Okay. And we just use the team Discord.
Discord,
Okay.
yes, yeah. Actually, no. It's a big blue button, but it's if you click on the link that I posted, the document that I posted, there's a link to the big blue button. The problem is with Discord, we were limited to 50 people in the voice channel, and we had more than that last year.
I mean, if they're double than us.
Yeah.
Oh, and we're less than 50.
No. Last year we had more, so that's why we decided to use Big Blue Button. This year I think will be okay. Especially because the Germans will be in their workrooms, I think. So there's like 4 or 5 people that use one login, then it would be a problem. So maybe today we could have used Discord, but we already changed to the big blue button, and it works just the same. It's just like Zoom and any of the other. So there should be a link, and you don't need to install anything. You can run it in the browser.
Oh yeah.
Okay. Let me just finish the matrix line with the actual